Hi, everyone. It's a pleasure to be with you all today. What I'd like to discuss is our recent work on galactic spurs of synchrotron emission and how we're starting to place new distance constraints on these structures. So let me begin by introducing these beasts of radio emission. This is an all-sky map of the radio emission at 400 megahertz. This diffuse emission is primarily of galactic origin. You can see the galactic plane in the center. And it's been well known for several decades now that there are features that emanate from the galactic plane and go out to very high latitudes. These features are known as radio loops or spurs, the most prominent of which is loop 1. Its brightest structure is the North Polar Spur down here. And despite their prominence, we still are unsure about what these structures are. When you look at these structures in polarized light, that's where most of the contrast is seen, and you can see these features much more clearly than in total intensity. And this is what I'm showing you here. Again, a map of galactic in galactic coordinates. The background color now is the polarized intensity of synchrotron emission at 30 gigahertz measured by Planck and WMAP. Loop 1 is this very, very well-defined structure that you can see over here, and there are numerous spurs that have been defined and outlined by Vidal and collaborators back in 2015. So again, as I mentioned, these structures dominate the high-latitude sky, but we're still debating what they really are. We know that the mechanism of emission is synchrotron emission, but we're still not sure what kind of event created them. And the original thinking was that these structures are nearby supernova remnants, but we'll see that the picture is a little bit more complicated than that. So I'll take as example loop 1 and sort of walk you through a brief history of what we've known or what we think we know about these structures. So loop 1 has a distance estimate that's still being debated in the literature. And there are two competing scenarios. One is that loop 1 and the North Polar Spur is an old and recently reheated supernova remnant. Combined activity from nearby OB stars and their winds and supernova explosions somehow created this structure in the very near vicinity of the sun, so around 100 parsecs from the sun. So in this scenario, the physical size of loop 1 is of order 200 parsecs or so. And its large angular size is explained just because it's very, very nearby. It's in our face. But there's a second scenario that posits a totally different origin and distance. In this scenario, scenario number 2, the galactic center actually is responsible for this huge structure that is now located at 8 kiloparsecs from the sun and has a physical size of 10 kiloparsecs or so. And these two scenarios have been the subject of recent reviews by a number of authors. So let me briefly walk you through the conflicting pieces of evidence that support each of these two scenarios. First off, we have stellar polarization, and this was the basis on which the first determination of the distance to loop 1 was made. What you're seeing here is again a map in galactic coordinates, but now all these lines come from stellar polarization measurements and show the magnetic field orientation as measured by stellar polarization. What was noticed early on is that towards the North Polar Spur, the stellar polarization angles seem to be tracing the outer edge of this much larger loop, not throughout the entire outline, but especially for this North Polar Spur region. And from this morphological alignment, it was concluded that loop 1 has to be within a couple hundred parsecs of the sun because these stars were nearby. In support of this nearby origin, stellar extinction measurements also show a very similar picture. This was demonstrated recently by Das and collaborators. Here on the left, you're seeing a composite image with red being the synchrotron emission at 30 gigahertz, and blue being the dust extinction, again towards the North Polar Spur area. These green circles show the regions in which Das and collaborators measured stellar extinction as a function of distance. And they modeled what the stellar extinction is doing in this space. So again, this is AV within this small region of the sky as a function of either distance modulus or distance up here. And what they found is that the stellar extinction fits well with the JUMP model that is located at around 100 parsecs or so. And so the extinction data and very old stellar polarization data show that the North Polar Spur is nearby. On the other hand, there's X-ray data that Constantina already showed us in the earlier session. And the X-ray data are telling us a different story. This is the recently published map by eROSITA, which shows X-rays from 0.3 to 2 keV. And the North Polar Spur is this bright yellow feature that you're seeing here in this composite image. And it's been known for a while now, even from measurements from ROSAT, so much earlier than eROSITA, that there's a molecular cloud that's causing the absorption of the North Polar Spur at these latitudes. This molecular cloud is called the Aquila Rift. It's at around 300 parsecs from the sun. And so since this molecular cloud is causing a shadow on the X-rays, it means that the X-rays have to be further than 300 parsecs. So that's a lower limit on the distance to the North Polar Spur. And to corroborate this kind of evidence, the eROSITA team presented this map that shows in red the gamma rays from Fermi, and in blue, the eROSITA bubbles. So by eROSITA bubbles, we see these blue structures in X-rays that appear to be centered around the gamma ray bubbles. And the surprising thing was that with eROSITA sensitivity, we were, for the first time, able to see that there's a southern bubble, a southern counterpart to the North Polar Spur. And so this morphological comparison led the authors to conclude that the North Polar Spur, and in general, the northern and southern eROSITA bubbles, are in fact placed at the galactic center and due to galactic center activity, just like the gamma ray bubbles. And so what I've shown you so far is that there are these conflicting sets of evidence that point to two very different origins and distances for the North Polar Spur. And the question is, how do we solve this inconsistency? And so what we tried to do is look at polarized light and look at it in detail in order to see whether we can get an answer to this question. So we know that the spurs are bright in synchrotron emission, and we know that synchrotron emission is polarized. So cosmic ray electrons spiral around magnetic field lines in our galaxy. And when they emit, their E vector of the synchrotron emission is perpendicular to the magnetic field as projected on the sky. And so if you measure the polarization of the synchrotron emission and rotate it by 90 degrees, you get the geometry of the magnetic field projected on the sky. And this is what is being shown with these lines overlaid on the synchrotron total intensity map from Planck. What's been known for a long time is that the magnetic field geometry is along the long axis of the North Polar Spur, Loop 1. Now we can use this geometry that is well known to pinpoint the distance to this structure along the line of sight by using a complementary tracer of the magnetic field. And this is done by using stellar polarization. So starlight is polarized due to an entirely different mechanism. Dust grains in the ISM are these non-spherical particles, and they get aligned with their short axis parallel to magnetic field lines. So when background starlight passes through this interstellar medium dust cloud, it becomes partially polarized in the direction that's parallel to the magnetic field projected on the sky. And so if you have stellar polarization angles for stars at different distances, you can sort of see the picture. The background stars will be polarized due to this magnetic field dust cloud. The nearby stars will be polarized in a different sense. So the idea is, if the synchrotron emitting feature is located at this distance, the background stars will have a polarization angle that's aligned with the polarization of this feature. So that's the signature that we're trying to find. To do this, we're combining two different kinds of data: the polarization of synchrotron emission on the left, and stellar polarization in combination with Gaia distances on the right. And we're going to do this analysis of comparing the polarization angles of these two mechanisms in these four regions along loop one. So here's what we get. For what I'm showing you here is a zoom in of loop one. This background shows you the polarized intensity. The red segments show you the polarization angle of the synchrotron emission rotated by 90 degrees. So this is the magnetic field of the synchrotron emission. And the yellow segments show you stellar polarization angles. And so we compare the polarization angle of stars and synchrotron within this circle. And this is shown here as an angle difference as a function of distance. Individual measurements are shown in gray, and we've binned the data in distance steps of 50 parsecs or so. And in this region, you can see that after about a distance of 100 parsecs, you get a much smaller spread in the angle differences, and all the mean values within the bins fall around 0 degrees. So we're finding a statistically significant alignment between these two polarization angles at a distance of around 100 parsecs. And this coincides with the jump of extinction seen with stellar photometry. So extinction as a function of distance and polarization angle as a function of distance shows that loop one has to be at around 100 parsecs, at least for this region over here. Now, at lower latitudes, the situation is different. In this case, we find an offset between the stellar polarization angles and the synchrotron. And this is because the stars are seeing a different magnetic field than what the synchrotron is seeing. And so for this lower latitude region, we can't pinpoint where the synchrotron emission is coming from. If you go to even higher latitudes, the alignment remains. So in these upper circular regions that we analyzed, there's a bit larger spread. I hear that, thanks. A bit larger spread, but still consistent with alignment after around 100 parsecs or so. The data are more noisy, but we can conclude that for these three upper circles, stellar polarization data show us that the synchrotron polarization also has to be at around 100 parsecs from the sun. For the lower latitude region, what's happening is that there's a longer path length. So what you're seeing here is a composite image of green, which is synchrotron polarization, blue, which is X-rays, and red, which is gamma rays. And so the lower latitude parts over here show X-rays that are absorbed and synchrotron that's depolarized. So there's a lot of overlapping features that are creating the structures that we're seeing here along the line of sight. At higher latitude, we know the synchrotron emission is nearby from this analysis. And we also see that the X-rays are very well correlated morphologically with the synchrotron. The synchrotron is sort of an outer envelope to the X-rays, and this has been known for a while now. And from this morphological match, we can say that at least some part of the X-rays has to be local within 100 parsecs of the sun. So that's where I'll leave it. And here are my conclusions. By using this joint analysis of stars, their polarization and the synchrotron, we can find, we can find where the synchrotron is along the line of sight. And from morphological correlations, we can sort of say something about the X-rays as well. I'll leave it at that and stop sharing my screen.
Thank you, Gina. Are there any questions for Gina? I see no hands, so let me go first. So Gina, you mentioned that the northern part, you are confident that it's very nearby, right?
Yeah.
But the southern part is not so certain. Do I understand this correctly?
Yes, this part has multiple things along the line of sight, as seen by the polarization of the stars.
Okay, what about, my question is, what about the rest of the loop? I mean, just to close the bubble. Any idea what's going on there?
It's a good point. We don't have stellar polarization enough to cover the entire loop, unfortunately. The sampling is very small, and so we can't conclude anything about that yet. With more data, as you know, we'll be able to make conclusions for that part as well.
Okay. There's one question by Vincent.
Hi, yes, I just wanted to ask you, Gina, if you can put constraints on the other loops. So you show us that there are many loops from Vidal, and one of those is eventually one of the interesting region is the Fermi region that we can see yeah, below loop 3 in this plot that we can see now. And so the question is, do we have enough starlight polarization data to put some constraints on the distance in that region?
So hopefully you can see, if you want low latitudes, there's a lot of stellar statistics in this map. If you want higher latitudes, not so much. The other loop we've been able to get constraints on is loop 4, but I didn't have time to show the results there. But yeah, as long as we have stellar polarization data within these regions, we could place constraints. The problem is, in the galactic plane, there's lots of stuff happening along the line of sight. So it's going to be tricky.
Okay, thanks.
There's another question by Joanna.
Hi, Gina. Thanks for the talk. It was very interesting. I was just wondering if you have any clues on the galactic column densities towards these higher to those regions that you studied, because I was thinking whether or not it would be possible to study some absorption spectrum in the X-rays over there.
Yes, that's a good point. So it's getting the stellar extinction, that gives you a limit on the column density, right? And then stellar extinction shows you that all of the column is within 100 parsecs at high latitudes. People have tried to model the column density using X-rays, but at high latitudes, there's very little extinction, and so it's very hard to constrain through the X-rays. At lower latitudes, it's easy to model the column density as a function with the X-rays. I mean, did that answer your question?
Yes, thank you.